This is the Math Map Book Club, where ordinary parents encourage one another to develop an extraordinary appreciation of math. We love what we know and struggle over the unfamiliar. Through weekly conversation and exploration among friends, we can begin to enjoy ideas that seem difficult. Join our book club as we discover how math helps us to know God and to make Him known.
Hi, I'm Lee Bortons, and it's Wednesday, November 20th, 2024. Welcome to the Math Map, where Kirsty Gilpin and I discuss lessons each week from our math curriculum for families with students enrolled in classical conversations communities. Well, it's Turkey Day next week, and I'm thankful that I'm not the turkey. And Kirsty, I really wanted to say I'm thankful for you and all that you've done for us over these last 2 years of book clubs, and for those of you that join week after week. So thanks again. And Kirsty, what are we going to do today?
We are talking today. I think I just realized I changed the number and not the title of our screen here. So I apologize for that. But we today are talking about triangles, not triangles and circles. That's what Babs did, intersected shapes. So forgive me, everybody, for not fixing that ahead of time. I said I was going to go back. So I will be thankful because Lee has always been so gracious and just exhibited such a great leadership of the Math Map team in developing what we have now are these published materials with more on their way. And she's just led us with grace. And I appreciate that. So thank you, Lee, for giving us the opportunity to work on this.
You're welcome.
So as we look this week at our math map, we always like to start here and say where we are. And so I have taken a page out of Babs's book last week to try and make this fancy. So we are here on lesson 17, nearly through the second dimension, but a couple of weeks into next semester. And we will be using the complex materials, but we always want to encourage you that you can be using any of the other domains that we've released, because we'll all be talking about the same concepts, even if we're using different numbers. So moving on to our exordium here and our interesting integers. I chose 26, but I will give credit to Babs, who sent me a fun article that was published in an art magazine of all things, but with some interesting numbers. And so I chose 26 for us to talk about today. So what do you see when you think about 26?
I was young then.
Seems like a long time ago.
Definitely an even number, so it's composite.
Multiples of 13, 2 times 13.
Just thinking about Babs's number last week of 30, that at 26, I think I felt like I was kind of getting my stuff together. I was an adult and I was doing things. But when we think about the fact that I wouldn't have been mature enough to serve as a priest yet, that's a good reminder that we're still growing and developing well into our 20s.
There's 26 letters in the alphabet.
It's about the age where the insurance rates start dropping on men. Is 26 the year that the kids can have to go off of your insurance? Is that 26? Okay.
Yep. How about anybody know of an intersection between 26 and the Bible?
Are there 26 books in the New Testament?
There are. Anything else significant about 26 that anybody can think of and want to share? Anybody want to come up with an expression that would express that number or share that number in a different base?
It's not exactly what you said, but if you add another 13 to it, you get 39, and aren't there 39 books in the Old Testament?
Ooh.
Maybe? I'm not sure. I mean, that's not part of 26.
So there's 27 books in the New Testament. So how I remember is 3 times 9 is 27, 39, 27. So there you go, Phil.
Good. There you go. Well, the thing is, we could go forever, and the students might want to do this some days and say, well, it's 2 10s and 6 1s, or it's 100 minus 74, or I mean, there's an infinite number of ways of expressing the number.
I found a
Yeah, it's
cool thing with the multiple of 13. So in 13, 1 times 3 is 3. And then 2 times 6 and 26, 2 times 3 is 6. And 3 times 3 and 39 is 9. Oh, it's kind of silly.
No, that's cool. That's a fun pattern. And that's what we want the kids to be encouraged, right? So just like Lee said, there's all these different ways. It's almost like a little bit of N2K in reverse, right? In N2K, we're given 3 numbers and asked to use those 3 numbers to compute a 4th number. Here, we're saying, look, you've got all the numbers at your disposal. What are some ways you could come up with 26? And so it's a little bit of a different mental exercise as we think through how we could express that. All right. Let's go ahead and take a look at our in our cover here. So this piece of art is by Vasily Kandinsky, and I would always have said I am not a modern art fan historically, but there's something about Kandinsky's works that I really enjoy, and I especially enjoy this piece of art that we have here. So let's go ahead and talk about what do you see here? Why might we have chosen this piece of art for this lesson?
You know how we say cacophony in music? When I look at this piece, I always think of the word cacophony. I know that's not probably the right term, but it just looks like, because they're all touching each other and they're overlapping, that it feels like cacophony to me, because I like things very orderly.
In foundations, when we talk about Pablo Picasso and abstract arts, and in this first 6 week, one of the exercises we teach the littles is always write your name and then draw lines through it and color each intersected shape, and that makes it abstract art. So I thought that might ring a bell if there are naturals fraction students.
What are some of the shapes that you see there that we've already talked about?
Circles,
Triangles,
squares,
Angles.
trapezoid,
Rings.
squares.
It's cool that even though there's a lot going on, there are parts you can name. And that could maybe be encouraging to us when we see a big word or a new idea, that it looks like a lot, but there are parts we can name. All these shapes that we're naming.
That makes me think of the kids looking at the charts. You know, that's like this. You can see some shapes or some colors you recognize in the cacophony.
When I see the half circles, it reminds me of the hops that we do on the number line. I probably never would have thought of that before had I not learned that through the math map.
There's a cosine wave. It looks 3-dimension, even though it's 2-dimensional. There's a cosine wave?
I noticed even though it says intersected shapes, there's various lines and open shapes. So I think when we think of shapes, we limit ourselves to 2 dimension, but you can have a shape even in 1D with just a line. It can just be a line. So I just see a intersection of a lot of the different things that we've already talked about up until this point.
Good. If we
Yeah,
were to
there are
think about,
parallel lines.
My iPhone's unavailable. Try again in 48 minutes.
what do you think that those shapes could represent? So if we were looking at that and thinking of it as representing something in the real world, what kind of story could you tell from this piece of art?
Since Babs said cacophony, you can kind of see music in it.
I think of the Phantom Toll Booth where you have the conductor conducting life.
Another one that we had studied was the composer is dead or something like that. We did that in foundation. And so that's kind of what that makes me think of. There's all this chaos that's building up to it. It's hard not to see music now.
I always think that the blue and the pink triangle especially look as though they could be mountains. And that sort of tilted on its side inside the blue mountains always makes me think of skyscrapers and a cityscape.
I look at this and I'm reminded of the dot and the line, another work by Norton Juster, just how the line manages to recreate himself in such a manner because he's bending, and I see all the different bends in the lines that are there. And yeah, I can just connect it to that story just looking at this, because it looks like you took all the pages from that particular story and just laid them all up, on top of one another. It might look something like this.
And isn't it Fra Angelico that does the halos?
Mm-hmm.
That's what the circles or the color that's illuminating from the circles remind me of.
What Dr. Gilpin said just now about it kind of remind her of nature. And this actually reminds me of a carpet that you will find in organic architecture, like Frank Lloyd Wright. As we take our kids to any Frank Lloyd Wright houses, to a field trip, you will be able to see some intersected shapes there.
Great.
You bring up the kids, it makes me think of what my table looks like when we've been doing crafts.
For left corner looks like an eclipse.
And those halves, the semicircle or the half moon shapes remind me of, or make me think of a studio audience, like the backs of their head.
I like that. So we haven't got there yet, but I'm going to encourage you just to look at this piece right here. I'm going to see if I can highlight it. There we go. And hold on to that. And either when you get off the call and you look at your booklets, go and look at the booklet for lesson 25. Or when we get to lesson 25, think about coming back and looking at this. And you'll see perhaps that particular piece of this artwork reminds me of the artwork for lesson 25. So I'm not going to pull that up. I'm just going to let you guys think about that, and you can investigate it, or we'll try to remember to come back week 25 and see if it reminds anybody else of the same thing. So great job. I think there's a lot here that makes this artwork accessible for our students. Even some of our students who maybe are less confident, hopefully can look at this and identify colors, identify different shapes. And it's pretty clear why this was chosen, right? Because there's a lot of shapes that are overlapping and intersecting with each other. So I always feel like this is a very accessible artwork for our students. So let's go ahead and move on to our invention page, our I² page here. And as we look at this page, I'm going to ask you to define intersection. What does it mean to intersect?
Cross.
To overlap. Maybe even to share the same space.
Okay, excellent.
Opposite of parallel.
Okay, good. Yeah, if we're in 2D and we're not parallel, right, and we're aligned, you've got two lines, they have to intersect. Good.
They could overlap in just one point. It doesn't even have to be a space. They could just have one point where they overlap.
Good. So there's at least one point that they have in common. Good. Where else have we talked about intersections? What other lessons?
Circles we talked about tangents where they overlap in one point. That's the point of intersection.
Okay, good. How about back in 1D? Did we talk about intersections in 1D?
Intersected lines. Don't we have lines?
So in 2D, we can have intersected lines. What did we,
Didn't
when we
talk about sets overlapping, like
yes.
union and intersection of sets of numbers?
Yep. And so when we talked about an intersection, we were looking at there was an and, right? We were looking at what are the elements that are in all of the sets, right? So again, this idea of something that's held in common, right? When we think about our students, what are some real world intersections that they might be able to grasp or visualize?
I think just driving two streets that intersect.
Crossroads, yeah.
So if you're in the middle of the intersection, which road are you on?
Yes.
Oh.
My road. My road intersect with others road. There's a concept between first person and then the third person.
Okay. But you're really technically on both roads, right? Even if I'm moving through the intersection, right? I'm on my road, but I'm also on that other person's road for a brief period of time, right? And so helping our students to grasp this idea that an intersection is a place where something is shared, right? That intersection is shared, the line is shared, the point is shared between two lines, or a portion of the plane is shared between two figures, right? That's when we're talking about our intersection. So I wanted to just touch on that idea that we did talk about this in 1D, and now we're talking about it in 2D, because it's important for us to see that these ideas are coming back around as we move through the dimensions. So continuing to take a look at our I² page, take a look at that middle piece there where we have the different colors. And let's think about an authority question. What do the colors in this section of the page tell us?
Maybe what belongs to which one so that we can distinguish.
Okay, good. So if I have two shapes and I've got two different colors, what happens in that third column?
Right. So the red and blue go together to make purple. So when they cross over completely, then it's purple.
Yeah, so that's not necessarily a mathematical idea, right? That's just a convention that we chose in the math map to help illustrate this for students, this idea of things being coincident or sharing the exact same space, because they're really the same thing, right? But we might define two things differently. And as we define two things differently and we want to say, oh, but they're really the same, they're occupying that same piece of space, color was one way we could do that. So we just wanted to share that because that's an important thing to understand, that may seem like a non-mathematical, but yet important concept. What dimensions are emphasized on this page?
Well, there's a lot of 2-dimension because we're looking at shapes, but then it goes down into the 3D intersections. So it shows perhaps maybe a connection between 2-dimension and 3-dimension and where we see that.
Good. Yeah. So we're looking at 2D and 3D. I brought in that idea of 1D, right? That's not on this page, but we can certainly help our students to remember that. And then if this is our first year through the math map, that 3D piece there is really just a look ahead. And do we expect our students to know what we're talking about there? No, but we want to emphasize this idea that we could have an intersection in 1D, we can have an intersection in 2D, we can have intersections in 3D, but what types of things can intersect is going to change, right? Can I have the intersection of 2 lines in 1D? No, there's only 1 line. Could I have the intersection of 2 segments in 1D?
So long as
Yes.
they're on the same number line, they're what did you say is coincidental?
They'd be collinear if they're on the same
Collinear.
line. Yep.
Collinear. Yeah.
Good. So those are some things as we get more sort of experience under our belt. Those are some ways that we can take what we're looking at and go a little bit deeper each year as we look at this I-squared invention page. Let's go ahead and look at our Memoria page. And I'm going to just use some of our grammar skills, our names here. What if I asked you to name the steps that are in the order of operations for simplifying, what are they?
Christy, are you asking about groupings, indices? Is that what you're asking?
That's what I'm asking. Yep.
So we would start by simplifying the groupings, which would be anything within braces, brackets, or parentheses. And then move on through simplifying indices. So looking at our powers and our roots, and then multiply, divide, add or subtract.
Good. So that's it, right? So when we ask our students to name, we're just saying, hey, let's use the correct words that we're using, right? We want to be very specific. Let's attend now. And if we were to attend to the order of operations for simplifying and solving, right? Let's attend to that. And what's some things that you might notice if you were attending closely?
They're opposite order?
Good. So if they're the opposite order, do they have the same, if we were to name the steps, we could still name the steps, right? We would just order them differently, right? But the steps are the same. Good. Let's take a look at this page and consider what is something on this page that you might memorize.
My challenge 8 kids would definitely pick the top. They would say, let's memorize this top section. Because that's more unfamiliar to them.
Good.
When I look down at the bottom though, below that area, it does look overwhelming. Like there's a lot of numbers when I first look at it. But if I focus on that left-hand side, I see a 1, 2, 3, and a 4 both are all with just brief instructions. So that's not really too much to memorize there in that area.
Excellent. So yeah, so when we look at this, it's important to slow down and not just shut down as we think about that. And to remember, we don't have to memorize it all in our first year. So Leslie, jumping off of that idea, looking at that 1, 2, 3, 4, right? We see there that there are these 4 different possibilities for the types of relationships that could exist between 2 equations. How could you express those?
I think I might need to make up some gestures that go along with that to make it interesting, but I'm not sure what they would be. Maybe even like opposite, our hands are pointing in the different direction and then come back together for same or something. I don't know how I would express coefficient. But then number 2, you'd be together for same signs and same coefficient. I don't know. I'd have to think through that a little bit.
It kind of reminds me of the 4 quadrants on the XY axis, because you have 2 different things that are either positive or negative or same or different, if you will. And so there's 4 different combinations of that. I don't know.
Yeah, I mean, and there's no right answer here, right? So when we're thinking about different ways to express something, I think you guys are coming up with some great ideas. Anybody else have anything they want to share there?
They're really getting into YMCA hand motions in my class, because we started that with some of the asymptotes and things like that, and putting movement with what we were seeing on the page. So now anytime I ask them stuff like that, I see kids put their arms up to do YMCA. So for the coefficient, you could do opposite sign with your hands on opposite sides and then go to Y every time for X and Y.
Yeah,
Are
so
you
there's right. Go ahead, sorry.
are you looking for any kind of expression or purely expressing in order to memorize?
Well, what do you have in mind?
Well, I've done it with playing cards before with my younger kids when I was working with, positive and negative numbers. So using, a red 2 when it's when there's a negative 2 as a coefficient, and using a black 2 when there's anyway. So just building it out for kids to practice would be one thing I might do.
Oh, that's great. So, and then our last thing is there something on this page that we could use to storytell or narrate the process for solving 2 equations with 2 unknowns?
Can you repeat that question?
Sure. So looking at this page, so not asking a student necessarily to pull from their memoria because they haven't really done this yet, but just looking at this page, is there a section of this page that would let them storytell or narrate, right? Use words to tell us what the process would be for solving 2 equations with 2 unknowns.
I'm certain there is, but I am driving at the moment.
Well, yes, Melba, don't you be looking then. So how about that row right under where it says solutions for 2 equations with 2 unknowns, right? If we read that, examine both equations A and B to determine the signs and coefficients. Then scale equation A or equation B to set up for elimination. Eliminate Y to calculate X by subtracting the equation B from A. Substitute X into equation A to calculate Y. And check by substituting X and Y into equation A or B. Is that a narration of the process?
So you mean just read the instructions?
Just read the instructions, right?
Are you trying to
So
say
I
we need to
just-
be reminded of that again?
Maybe, right? And so
When
there's a lot of
all else
places
fails.
when all else fails, yes, right? So these name skills, right? The names that we have are, I just think it's a good thing to remember that we can come back to those. And as adults, oftentimes we may want to overcomplicate it, right? And we think it's got to be more. But with our students who are looking at something that's unfamiliar, really encouraging them that it's okay just to go through and say, I'm going to read these names. I'm going to attend to what's different between these two. I'm going to narrate by reading the steps. That it doesn't have to be, it's not intended to be dialectic, right? It's really intended to be grammar, a grammar skill that all of us can use, right? So all of you who are thinking, I don't know how I'm supposed to solve two equations with two unknowns, right? All of you had access to that row, and it's okay to say, hey, I'm going to read this in order to narrate what we're doing. And to encourage our students, right? That's where our learning begins. So let's go ahead and take a look at our charts. And as always, one of the things we want to do is talk about what is familiar and what might be unfamiliar, but interesting on these chart pages.
The train.
Well, I can see what came from the frame, top right. And I can see all these curves on the bottom right that I keep seeing over and over again in the lessons.
Yeah, so we've seen these list of functions. We saw them in 11. We saw them listed in 13 different graphs, but we still saw the same list. We see them here again in 17. We're going to see them in 18, 25, 26, and 30. So that should be starting to be familiar. And remember, familiar doesn't mean mastered. Just means, oh, I've seen that before. What else is familiar?
The inscribed and circumscribed circles.
Good. How about the names of those figures along with their measures on chart 1? Are those familiar?
I was gonna say, we've been working on similar problems since like middle school years.
We have, and within the math map, right, those we looked at those in weeks 12 and 13. So notice that there's a lot, this week especially, I think is one of the most reviewish kind of a weeks, because we're taking all of this information that we've seen before, and charts 1 and 2 especially are really a summary of a lot of the things that we've done from weeks 9 through week 16. And then we're going to take on charts 3 and 4, we're going to look, okay, how do we take all of this information? And if we had more than one thing, how do we look at where it might intersect? So I just want to encourage you that a lot of the information here should feel familiar, not mastered. You may not remember all the details, but hopefully you can encourage your students, like, you've seen these words before, you've seen a lot of these images before, right? And so there's not new grammar on that in that respect this week, but we're taking this and we're reviewing it. And it's also a great example of just how much review is built into the math map, right? Even though it may feel like, oh, each week we've got this new concept, we're always coming back and pulling in things that we've studied previously and looking at them either from a new dimension or a new aspect, right? Something that we're going to do with them. So I just want to encourage you that there's always this sense of repetition throughout the year, as well as from year to year as we move through the math map. Anything else anybody wants to share as we look at the charts? Where, again, just thinking back, where, what lesson did we first think about intersected lines? If you look on your math map, you'll see that there's a lesson called Intersected Lines.
Lesson 10.
Lesson 10, right? So here we're looking at intersected shapes. We're taking that idea of intersection and taking it a step further. But if you as a parent or a tutor wanted to go back and see what did we say about intersected lines and how might that help us in intersected shapes, that would be a good lesson to go back and review. I just wanted to point that out. All right. So specifically for week 16, does anybody have a testimony or a question? Right. So let's go ahead and take a look at the first couple of pages here together. And as we do that, I left Babs's exhortation here to read the directions. As we look at these shapes, I'm going to encourage us, right, to actually think beyond, before we get into reading the directions and doing what we're told here, just to take a look and attend closely. And what are some of the shapes that we are dealing with?
Squares, circles, rectangles.
Triangle.
Triangle.
Triangle, good.
These are
The
all
other,
comfortable shapes.
good. Yes, I know. It's nice when they're like, oh, I'm familiar with this. So then looking at those grids, right? So we're doing all of these things on a grid because it's going to help us to determine sizes and so forth. We'll look at the grids, and I want to point out our scales are not always 1-to-1. What are our scales on each of these?
It's
a unit of measure.
Right. So on that first one square of my graph is how much? How much does it represent?
2 inches.
2 inches. How about on the second one? What is 1 square?
1 foot.
1 foot. And the third one?
2 meters.
2 meters.
2 meters.
And our fourth one?
2 inches.
2 inches.
2 inches. So it's important for us to help our students to attend to those details because it would make a big difference, right? Especially if we were to take a diagram like this and move it into the real world and want to build something, right? That scale would really matter. Is there anything on here that may feel familiar from week 12? Where we were taught, no, we haven't done. Have we done? all of my weeks are blending together. So I'm going to make sure that I don't say something wrong here, but I think it's in week 12 where we talk about nets, but it's not.
Well, is week 12 the one where they've got the graph and then like triangle shapes inside it and you subtract those out to get the remaining area? Is that what you're talking about?
That's good. That is an excellent point. I'm actually thinking about something from 3D. So I suddenly realized as I was going there, I was like, I think that's actually a 3D lesson. So I won't expect that, but what you did pull out was excellent, right? This idea that I can add and subtract to find areas is exactly what we're doing here. So now let's read our instructions, and our instructions say to simplify and then leave the solutions in terms of pi. So let's take a look at the first one here. And again, I want to just emphasize, because we've had this question from a couple of people. If I have, right, my A is my area, so that letter is a variable or a parameter that's saying what it's representing. When I add a subscript, what I'm doing is I'm either identifying specifically what that goes to, or I'm identifying a specific value of it typically. So here it says the area that's shaded. And you're going to see that we're going to have other places where you might see something like A with a subscript of a T. That usually is just representing the area of the triangle, right? Or the area of like maybe it's square. Or you might see where it's actually drawn with a triangle. So I just want to point that out, that subscript is usually just identifying information that goes along with whatever it is that we're trying to measure with that variable or parameter. So in this case, we're told that the area of the shade is s squared plus pi r squared. So as we look above, right, what shape does that s squared go with?
Square.
The square. And how about pi r squared? What shape would that be the area of?
Circle.
A circle. So now as we look above, we see that my side is 8 inches, so that's been substituted in. My radius is 2, so I've substituted that in. As I continue to simplify, I see that I have 64 inches squared plus 4 pi inches squared. And then I really want to emphasize that even if you have students that, right, we're not at all ready to undistribute or factor out the units, what we can do is use this pattern where we see I took the 64 and the 4 pi and I put those inside my parentheses and I put my units outside my inches squared. And this is where we stop, right? Now, if you want computation practice, you can have your students substitute in an approximation for pi. You could use 3.14 if you want to practice multiplying with decimals. You could use 22/7 if you want to practice with fractions. But we're asking you just to leave things in terms of pi because that is the exact answer. Okay, so I just wanted to point that out, that most of the time we're leaving things in terms of pi or the square root of 2 or whatever it is because it's the exact answer. As soon as we put in an approximation for those irrational numbers, we have an approximate answer. But this is one way at home. If you're looking for more computation practice, you could put an approximation in there in order to have that computation practice. So let's go ahead and look at the next one. What shape does length times width go with?
A rectangle.
Our rectangle, and pi r squared, we've said, was our circle. So now as I substitute in my 6 feet and my 4 feet and my 2 feet, and I multiply through, I get my 6 feet times 4 feet is 24 feet squared. Pi times 2 squared is 4 pi times feet squared. And so what part is going to go inside my parentheses?
24 plus 4 pi.
And what's going to go outside my parentheses?
Feet squared.
Feet squared. Good.
Would it be wrong to also factor out the 4? So it's 4 opening parentheses 6 plus pi closing parentheses feet squared?
You could, you certainly could. I don't think I would, because I'm just looking for that numeric piece to be together, and my units to be separate. If I was solving for a variable, then I may want to do that. But I don't know that factoring out the 4 is going to really change, right? It doesn't give me any more information. So I would just leave it at this point here.
Thank you.
You're welcome.
I think that's the most difficult problem with math solutions is everybody says they like math because it's always the same. There's an infinite number of forms for any solution. It really isn't always the same. And it's just more the convention. What we've taken is the form that you start in is where we try to end. Unless we say convert.
All right, let's look at our third one here. So we've got, again, building off of what we had length times width and pi for our rectangle and pi r squared for our circle. But notice here, this was an addition problem because I have two shapes that are being added. Notice here, why do I have a subtraction problem?
They're looking for the area of the shaded portion, and so the circle is not shaded.
Good, excellent. So there's something that we can notice. Again, all right, the level that you go to with your student, you don't have to ask all of these questions, but I'm trying to model, right, that there's a lot of different ways we could approach these page tops to go a little bit deeper, or just to have our students look for the pattern and finish the problems. So as we do this, we have our 8 meters times 6 meters. How do we know that? We're not given the measurements this time. So what did we have to do? We actually had to read it off the graph, right? So I have a half plus 1 plus 1 plus a half. That would give me 3 times 2. That's my 6. And I have 1, 2, 3, 4 squares times 2. That gives me my 8 meters. When I multiply those, I have 48 meters squared. This time I'm subtracting pi times 2 meters squared. And right, so we see here that this radius, because it's the same, I can look at this part right here to know that my radius is 1 times 2, which is 2. So now when I subtract this, what's going to be inside my parentheses?
(48 minus 4 pi).
Good. And again, we can help our students see, right? The pattern is still the same, but now we have a different sign. So that sign has to come in, and then my units are outside. And then our last one, what would be our simplification for the last one?
Minus 9 pi.
Good. Right, so this is a pre-algebra skill that we're doing right here. We're not calling it a pre-algebra skill. We're not telling people this is a pre-algebra skill. We're not saying they're factoring out. We're just asking them to follow a pattern, right? But eventually this same pattern is going to be, imagine if this was, right, not necessarily in this lesson, but in monomials and into binomials, right? If this was an x squared instead of an inches squared, right? That I can start to see what that looks like, right, when I'm taking out a common factor. So I just, again, pointing out all of these ways that here it seems like this, we're just looking at this pattern, but as students become familiar with this pattern, they're going to eventually be able to abstract that in order to apply that algebraically as well. So let's take a look. This page is a little bit different to the first one. Now we're looking less at the shapes and those intersections and how we could calculate their areas, and looking at the way that things might intersect. And so there's some hints here. There's only one word that is used here that's not already on this page. So let's take a look first, and we're told to describe the shape. And we're told that the first one is linear. So what does that, and then we're given L's here for our second and third. So what shape are our second and third columns?
Linear.
They're going to be linear. Good. And so here's a place where, again, right, we're using these patterns, and even if students don't remember that linear is describing a line in this case, right, we're starting to see this pattern, so that when we look at our fourth column, right, and it says it's nonlinear, what kind of lines do we have here?
Curved lines.
Curved lines, great. So our second row asks us to find the number of intersections. We're told that there are 0 for the first one. How many intersections for the second one?
1.
1. How about our fourth one? How many intersections between our two curves?
2.
2. Right, and so those we can count, and we've got those hints. Let's look at that middle one there, because that's the one that may be the most challenging as we look there. How many lines are there in each of these boxes?
2.
2. Are there 2 lines in this box also?
Yes. Yes.
Yes, but one's lying on top of the other one. So how many points of intersection are there?
Infinite.
Infinite.
Excellent. And then our third row, we might want to do some comparison here. Our first column, where we had 0 intersections, was inconsistent. Our other columns all have intersections, and 2 of them are written as consistent, of a C for this second column. So what do you think that one is going to be?
Consistent.
Consistent. Excellent. Now we could have looked at the chart also to help us figure that one out, but just by using what was on the page, we were able to come up with that. So let's go ahead. I just want to remind everybody that we want to finish our week by our logic catechism, remembering that we want to continue to practice what those skills are. And then I am going to mute myself for a minute because I have a child that's called me for the 3rd time. And then I'm going to ask Lee just to talk about what we have coming up in the next couple of weeks.
Sure, I'm happy to. So obviously we aren't meeting next week because it's Thanksgiving, but December 4th, 11th, and 18th, where we have the Q&A, we think it'll go a lot better if you can email questions to us ahead of time. The other thing that we can do is, Babs, if you and Shauna want to get us some frequently asked questions that are maybe easier to explain with a voice and a face, we can go over those also. So we look forward to December being just without an agenda. And if nobody wants to talk about anything, we'll just sign off. Okay. And I can't move the screen, but I know the next thing we do is it is time for questions. So if anybody wants to ask the first one, or if there's something in the chat that we haven't been answering, go ahead and put it back in. So have you been following it, Shauna or Babs?
I
Yes,
haven't seen
the
any.
questions, right,
Yeah, I
the
haven't seen
questions have been answered.
Okay. Or anybody else? And of course, you can back up to week 16 or earlier.
I have a question from I think it's naturals. This is crazy. Week 13 in naturals on page 16. at the top, it says trace and color and trace and color. And one is kind of like a apple shape or a bloated heart shape. And the other looks like the same bloated heart shape, but with a circle inscribed or not inscribed, but inside it.
Uh-huh.
And it's a limacon. And I guess I know we're just supposed to start getting familiar with this, but that would be more like a heart, right? Versus obviously the Star of David. But can you explain where like limacons come from?
Oh, I'm glad Kirsty's back because I know to me, all they are is you're plotting an equation and ooh, the equation makes a pretty shape.
That's weird.
So so if you look on lesson 13, if you look at the chart for that lesson, chart 13.4, when we're graphing with polar coordinates, and so that's where I say, okay, I'm going to use my angle measure as my independent variable and my radius is my dependent variable. As I look at the graphs that I can create there, they're very different to the graphs that I would get if I was plotting something in a rectangular coordinate with X's and Y's. And that's where I get a lot of these fun curved shapes. So those, when we're using sine, cosine to graph our polar coordinates, we can get roses, the limacons, and the lemniscates, and that is what we're tracing there. And so you'll see if you look on the chart, you're going to see what those equations look like. And they're just really fun equations because they do give us these really cool shapes that we can examine that are all based off of angles and radius. Does that give you enough information to get you started?
Well, sort of, but I only have the downloadable natural, so I don't have the charts. That's why I was
So you do actually, if you have access to CC Connected, if you go to the companion and you click on even in the complex, right? So I know you can't download it, but you can actually look at the charts by going and clicking on the complex booklet. And so if you click on the complex booklet for week 13, you can actually flip the pages to the charts and you'll be able to see those equations there.
I am so sorry, Kirsty. You are so right. And there's an intersection between, okay, doing the complex with the CC companion and then trying to do naturals all by myself. I just intersected those two with your help. Thank you so much.
Oh, glad we could do that.
And some people have asked me, like, they see something in naturals or in complex they've never seen before like that, and are wondering, am I expected to know this and master it before we start doing equations for the high school years? And I just want you to rest assured that these are really fun art projects. There is an equation that they'll solve, but for when they're challenged 2, 3, 4. But for now, what you're seeing, it's really grammar and art, and this is the extent of expectations.
Well, thanks everybody for being here. And I'm really excited about our 3 weeks in December when we're just going to be able to jump on and answer questions. Hopefully we'll have some people who may be in community on Wednesdays can join us live. But if not, you can also email questions to us beforehand and we will do our best to answer those on the book clubs those 3 weeks. So thanks everybody. It's been great spending time with you this week.
Happy Thanksgiving.
God bless you all. Happy Thanksgiving.
Thank you.